welcome the in-person talk. Okay. So today we'll be having Dr. Jeong San.
Jeong San.
Jeong San.
Right.
He's a professor of mathematics and the leader of the quantum computing lab at Calgary University, Korea. After his PhD from Seoul National University in 2006, he was postdoctoral research fellow working with Prof. Barry Sanders and Prof. Gilal in the IQIS at UFC. From 2011, he was faculty member in the Department of Mathematics at the University of Suwon, Korea, and he got his current position at Kyung University in 2009 to 2015. His research interest is the mathematical aspect of quantum information and computation theory, including various properties of classical and quantum correlation in multipartite quantum systems. And recently, also, he's working on quantum non-locality arising in quantum state discrimination. And today we'll be talking about locking and unlocking non-locality without entanglement by post-measurement information. So let's welcome Prof. Kim.
Thank you. So as Naha mentioned, I'm going to talk about locking and unlocking non-locality without entanglement by post-measurement information. And this is a joint work with my postdoc, Dong-Hoon Ha. So this is the outline of my talk. So first, I'm going to talk about quantum state discrimination, as well as the concept of non-locality without entanglement that might occur in discriminating separable states. Then we'll talk about what kind of post-measurement information we'll use here, as well as the state discrimination when the post-measurement information is available. Then we'll formally define the concept of locking and unlocking non-locality without entanglement by post-measurement information. Then we'll see some examples of locking and unlocking NLW by PI with detailed calculations. And then I'll summarize. Yeah. So let's think about the situation. There is a set of states. Can I use pointer or? It wouldn't work to this screen, right?
First time we've ever been here. We don't know.
Okay, I see. Yeah. So let's do this. Okay. So let's think about the situation. We have a set of states, rho i's, which is known to us. No, I'm fine. It's okay. Okay.
Trying to solve the problem.
Okay. Yeah. And let's. Yeah. Should I keep going? Okay. So there is a set of states, rho i's, and the probability distribution, eta i's. Okay. These are already known to us. Then, with respect to the probability distribution, one of the states of the set will be prepared to us. Okay. And the task of quantum state discrimination is to guess what is the prepared state. Okay. And as we have this set of states, as well as the probability distribution, we can think about this as an ensemble, okay? State ensemble with probabilities eta i's and state rho i's. And I'm going to use this expression, state discrimination of an ensemble epsilon, which means this case. Okay? So what we need to do is to make a decision rule to decide what state is prepared. And as we are dealing with quantum states, so the only way we can get the information about the state is by measuring the state. Okay? So we have these measurement operators satisfying this positivity condition and completeness. And the decision rule we are using here is following. If MI is detected, then we're going to decide that the prepared state is rho I. So no matter what the actual prepared state is. Okay? And the probability of detecting MJ when rho I is prepared is, as we know, this is the inner product of these two operators.
Is everything finite dimensional?
Yeah, we are talking about finite dimensional system. So if you think about the average probability of correct guessing, or success probability in short, which is nothing but the expectation of the probabilities with row I prepared and mi detected. Can you see in the back? Okay, sure. So yeah, the expectation of the probabilities with same indices. Okay? And the guessing error, which is nothing but the complementary probability, is the expectation of the probabilities with different indices. Okay? Because PF, yeah, as mentioned, we call this as the success probability. Of course, with respect to these measurement operators, this POVM. Yeah, trivially, this success probability is between 0 and 1. And if this is equal to 1, that means perfect discrimination is possible. Okay, we can perfectly discriminate the state. But we also know that this is possible if and only if the states are orthogonal to each other. So we can only perfectly discriminate orthogonal states. Right? So more precisely, there exists POVM realizing this perfect discrimination, and it's if and only if they are orthogonal to each other. So in other words, if they are non-orthogonal, some of them are non-orthogonal to each other, then we will never achieve this perfect discrimination. So in that case, we are interested in what is the best we can do. What is the maximum success probability? Okay. So the minimum error discrimination of the state ensemble epsilon is nothing but to maximize the success probability of all possible measurement, POVM. Okay? And the maximum success probability is also called guessing probability, and we will denote it by PG. So here G is for guessing. And also we can think about it as the general measurement. There is no restriction on the POVM.
Do you have a typo in your, like you wrote in the first bullet, it says calligraphic E equals the set, and you have E to I, row I, and then you have an I on the outside. Should that be just the number n?
Which one are you talking about?
It's gone.
It's gone.
Still gone.
So the slide you were on earlier.
Yeah, the next slide actually.
That's one.
Yep.
No.
Next.
This one?
One more.
Same one.
Okay.
It's back.
The first line, the top line on the top.
So which page?
This one on the top.
This one.
Okay,
The
you
top.
have I. That confuses me. There's no I in the left.
Oh,
That
yeah,
must be the
sure,
number.
yeah. Must be the number, this one.
Yeah, okay.
Okay.
I just asked, that was a
Thanks
typo.
for correcting me. Okay.
Not correcting, querying
Okay,
correctness.
see.
Yeah, okay.
So where were we? Yeah, the reason why we put G is for guessing, but also it means that there is no restriction on the measurement. We can think about any general measurement. Okay? Yeah, so because the guessing probability is optimization problem. So if we want to have this actual value, we need to solve these optimization problems, which is generally very hard, and it's known to be NP hard actually. So it would be better, it would be good if you have some.
Sorry, whoa. You said NP hard. Okay.
Yep.
So you're maximizing overall POVMs. When you
Yep.
say it's NP hard, I need to know.
So I mean, generally, this kind of optimization problem is known to be NP hard. I'm not talking about the specific problem.
But what would be the size? Is it the log of the dimension of Hilbert space? Is that what you're looking for the scaling?
Let's see.
So I'm trying to quantify the size of the problem.
Okay. So it depends on the size of, so actually the dimension of the Hilbert space.
Log of dimension. Yeah. It's
I mean,
exponential with
it's
respect
log,
to.
yeah, log of the dimension.
Okay, I'm satisfied.
Yeah, so this proposition is about the optimum POVM, the property of optimum POVM that realizing this guessing probability. So it's like this. For the minimum error discrimination of this epsilon, if a POVM realizes this POVM realizes this guessing probability, and it's if and only if that POVM satisfies these properties. Okay? So each j in lambda is the index set. So this operator needs to be positive semi-definite. Okay. So if we can find some POVM satisfying this one, then we can get this guessing probability by taking the expectation with respect to this measurement.
Sorry, PG was optimal.
Guessing probability. Yep.
But that was optimal, and then this looks like, yeah. So the PG is the maximum overall
Maximum
POVMs.
value,
Is that
okay.
unique, or is there more than one maximum?
This value is unique.
Unique, but then on the
Yeah.
next slide, you
This one
say,
is unique, but this one doesn't need to be unique. There can be more than two.
no, that's what I'm asking. So I thought, so you're saying, like this, that's a majorization, or
No, positive.
positivity, okay,
Positivity,
non-negativity.
non-negativity. Okay.
So you're, and you're
So
summing
your
over
question
I,
is whether this one is unique or not. This POVM, realizing this PG.
and you're saying it's not.
No.
Okay.
Yeah.
Yeah, okay. Yes.
But any POVM realizing this guessing probability must satisfy this condition.
Okay, and you've changed, yeah, I asked you before
Oh
about
yeah,
that.
sure. Yeah, this one is.
You had
from
n
1 to
before,
n.
and now it's lambda.
Yeah, lambda, just index set.
What? Oh, but it's a different
Index.
set.
Oh yeah.
Where did it come from?
So
It has,
yeah.
it already has.
Okay, lambda is the set of numbers from 1 to n in this case.
Oh, okay.
Yeah.
You don't need a board for that.
Okay,
Yeah, but in case you need it.
thank you very much. Yeah, I'm not going to need this.
Yeah, it has the.
Thank you. Okay, so this is a kind of a good theorem to guarantee whether the given POVM realizes this guessing probability or not. And we're going to use this one later. Okay, so the guessing probability is the maximization over a possible POVM. But if we can also think about some restriction on the measurement. So if you think about the maximum over LOCC measurement instead of any general measurement, then we can also think about the maximum. We will denote that maximum over LOCC measurement of the successful probability as PR of epsilon. Okay? And of course, LOCC measurement is the measurement that can be performed by local measurement and classical communications. Okay? And by definition, it's clear that PG is always larger than or equal to PR. Because the set of LOCC measurement is a proper subset of a general measurement, set of general measurement. So now we are ready to define non-locality without entanglement. As following. So we are thinking about separable state ensembles. Let's say this epsilon is a separable state ensemble. So for each I, rho I is a separable state. So there is no entanglement in this ensemble. And we think about PG, the guessing probability of epsilon, and also PN, the maximum probability of our LOCC measurement. And sometimes these two are equal to each other. Actually, we have this trivial inequality. But what I want to say here is that sometimes we can have this strict inequality. Okay? So as mentioned before, there is no entanglement in this ensemble. But only with LOCC measurement, we will never achieve the guessing probability, the global optimum, global maximum. Actually. So, which means there is some non-locality, which we cannot do only by LOCC measurement. That's why it's called there is non-locality in discriminating this ensemble, but there is no entanglement. So that's so we call this as non-locality without entanglement, and discriminating this ensemble. And if this is the case, equality is the case, then we say that there is no non-locality without entanglement, or briefly NLWE in this ensemble. Okay? So we are clear with the definition of non-locality without entanglement.
Why have you got O and X? What am I-
Non-locality, NLWE occurs.
What?
NLWE occurs. There is NLWE.
Oh, so occurs is
It
O,
occurs.
and X is,
Does not occur.
okay, got it.
Right. So to check whether there is NLWE or not, we need to think about the values of PG and PR. So as mentioned, PG is hard to get. The actual value of PG is hard to get, right? Because it's an NP-hard problem, generally. And what about PR? This is a maximization of all possible LOCC measurement. And it's even harder because, there's not really good mathematical characterization of LOCC measurement. So we don't really know how to do this. So sometimes it's very useful to get a good upper bound of PR.
So it's even harder, you mean, so which, like, there's computationally hard, there's computability, there's the question whether it's algorithmic. So what do you mean when you say harder? Do you mean there's no algorithm? It's not computable?
Maybe mathematically I can say like this. The set of all POBL is closed, topologically closed. But the set of all LOCC measurement is not even closed.
I don't know why that makes it harder.
So like this, there is some distinction between LOCC and asymptotic LOCC. So there are much, complicated things.
Right, so closed just means it's complete, right? That every Cauchy sequence converges to a point in the...
Yeah, that's closed.
Okay.
That's complete actually, yeah, that's closed, yeah.
Right, so you're saying that one is closed, the other isn't?
No.
You're not saying?
You're right, one is closed, the other one, set of all LOCC measurement is not closed.
Right, okay, so that I understand, and I don't know, but when you say harder, I don't know why it makes it harder.
So it's like this, for the case of LOCC measurement, so we are not even sure whether there is maximum or not, because the set is not closed.
But can't you then define a supremum?
Yeah, but the case of our consideration, it's not the case. I mean, we can find the maximum.
Okay, so what you're saying is that you don't know if the limiting point is in the set.
No.
So even when you do the convergence, you don't know that it converges to an allowed point. So it makes it not even computable because you have to just keep proceeding. Okay, so your hardness is a computability hardness, not a complexity one. Is that right? You can tell me tomorrow.
I can really follow the last one you said.
Well, you say harder, and I'm asking if it's
computationally hard. Does that mean?
But that's complexity.
Okay.
But then if you don't know if there's a solution unless you keep going forever,
Oh, I
then
see.
it becomes a computability problem. So I'm asking which one you mean.
The second case.
So
the second one.
So you could be saying that the LOCC version is not even computable in a technical sense. Is that right?
Yeah.
Okay, that's interesting.
Okay. Right, so we have the definition of non-locality without entanglement. And we were talking about the upper bound of PR. So it's, as we discussed, computing PR is very hard. So sometimes it's very helpful to have a good upper bound of PR to check the non-locality without entanglement, to check actually this inequality. Okay? So, this proposition 2 is about an upper bound of PR. So if there is a Hermitian operator H satisfying that every operator here, H minus eta I rho I, where eta I rho I is from the ensemble epsilon, if this one is in this SEP star, self star, which will be explained later, for each I, then the trace of H is an upper bound of PR. This is known. So let's think about this set. SEP is the set of all positive semi-definite separable operators. Okay, so it doesn't need to be normalized. Okay, it's rather than just complex set. It's a complex cone, right? And this SEP star is a dual set of set. So it's the set of every operator having this non-negative trace with every B in this set. Okay? So for each I, if this operator is in this SEP star, then this H, the trace of H is an upper bound of L. It's already known.
Is that Sam Shugrove or a different S boundary project?
Which one?
The article 4, is that Sam Shugrove?
Yeah. He used to be here.
Yeah, at the same time as you.
No, he's gone before I came here.
Okay.
I've never met him actually.
Oh, okay.
Right. So we're also going to use this one later. So, okay, so let's talk about post-measurement information. So, for simplicity, we're going to think about these ensembles of 4 states. So there are 4 states, row 0, row 1, and row plus, row minus. And the reason why I use these indices, 0, 1, plus, minus, instead of 0, 1 to 3, is because we're going to make some distinction between these 2 and these 2, right? So the index set lambda would be 0, 1, plus, minus, and of course the corresponding probability of preparations. Right, and the distinction is actually sub-ensemble. So with these 2, row 0 and row 1, we'll think about the first sub-ensemble, epsilon 0, say epsilon 0, and these are the normalized probabilities. And with the last 2, row plus, row minus, we'll think about this second sub-ensemble, epsilon 1, and also normalized probabilities as well. So the situation is like this. The preparation of row 0 from ensemble with this probability at the 0 is equivalent to say, we first pick the first sub-ensemble, epsilon 0, with this probability, and we pick row 0 from this first sub-ensemble with this conditional probability. Can you see this? Okay. So yeah, these are equivalent to each other. Yeah, and the post-measurement information we're gonna use here is the information about the sub-ensemble, in which the prepared state row I is from, right? So if the post-measurement information is 0, that means row I is in epsilon 0. That means row I is either row 0 or row 1. And similar thing is true for the case of case when B is 1, right? Then row I would be either row plus or row minus, okay? So we know that we're gonna get this post-measurement information after we measure, right? So what we need to do here is to determine what the prepared state is with the measurement outcome together with the post-measurement information. So are we clear with this? So if you want to use this post-measurement information wisely, then we may think about what kind of measurement we need to do here. So the measurement should detect one state from each sub-ensemble. So we need some measurement which determines, say, row 0 in the first sub-ensemble and row minus in second sub-ensemble. Okay? Then together with the post-measurement information, which tells me which sub-ensemble, we can determine whether the state is row 0 or row minus. That's what we're gonna do. Okay? So I'm going to use this vector notation as the index here. So M0 plus minus, M0 plus means that this one detects row 0 in the first sub-ensemble and row plus in the second sub-ensemble. So the measurement outcome is this one. And if the post-measurement information is 0, then we are just interested in the first coordinate, 0. Okay? So row I, we will guess row I is row 0. And the other case, if the post-measurement information is 1, then we are interested in the second coordinate, plus. Then we may guess that the prepared state is row plus. Okay? We'll think about this kind of measurement. Or we need to use this kind of measurement to use this post-measurement information wisely. So for the vector notation, I introduced some other notations here. So A0 means the indices set of the first sub-ensemble, 0, 1. And A1 is the indices set of second sub-ensemble, plus and minus. And then the set of indices is just the union of these two, A0, union A1. And we also define this omega as the Cartesian product of A0 and A1, so that we have these vectors in this set omega, right? So these are 0 plus 0 minus, 1 plus 1 minus, 4 indices. Okay? So for example, if this one, M0 plus, will be denoted as M omega, the vector omega, where the vector is 0 plus in this capital omega set. Yeah, then the measurement outcome would be these vector indices, and together with the post-measurement information, we may guess what the prepared state is. Okay? And so now let's think about the probability of correct guessing when the post-measurement information is available. So for the case when the post-measurement information is 0, then the success probability will be the case when row 0 is prepared, we need to detect either M0 plus or M0 minus. Both of them have 0 on the first coordinate, right? And for the case when row 1 is prepared, we need to detect M1 plus or M1 minus. And both of them have 1 on the first coordinate. Okay? Then we can sum of these two for this into this single summation, and these two into this single summation, and we can also sum up these two to get this one. Just to use this indices notation. Okay. And a similar thing is true for the case when the post-measurement information is 1, right? A similar thing we can do, and to get this average probability. Then the average probability of correct guessing, success probability with post-measurement information is nothing but the addition of these two. The case when B is 0 and B is 1, right? So to obtain these a bit ugly summations, okay? And we can think about the maximum possible success probability of our possible POVM when the post-measurement information is available. So we'll denote this as PGPI, which is the maximum of our possible POVM of this success probability, right? And we can also think about the maximum of our possible ROCC measurement, which we will denote as PLPI, okay? And of course, this one is always larger than or equal to this. And we are interested in the case when the strict inequality happens. So this is the definition of NLWE with post-measurement information. When the post-measurement information is available, if we have this strict inequality, then that means the LOC's measurement cannot achieve the global optimum, right? When the post-measurement information is available. So we call this NLWE with PI. And the other case is the equality. That means there is no NLWE with PI. And now we are ready to define what locking and unlocking NLWE by PI is. Okay? So for the separable state ensemble epsilon, so there is no entanglement. And the sub-ensembles, so the PI, we say that PI about the sub-ensemble locks NLWE. If there was NLWE in the first place, for the case when there is no post-measurement information, but if post-measurement information is available, then the NLWE vanishes. So that's why we call this PI locks NLWE. Okay? And unlock NLWE by PI is the opposite case. Right? In the first place, there was no NLWE, but with post-measurement information available, we have this NLWE. So that's why we call unlocking NLWE by PI. So are we okay with this definition? Right? Okay. So before we see some examples, let's think about the relation between state discrimination with PI and state discrimination. So for the case when the post-measurement information is available, we got this average success probability, okay? And what we're going to do here is to expand the gain. So this one is actually obtained by adding these two success probabilities when PI is 0 and PI is 1. And the first row was actually how we obtain this PS0. This is the first row. And PS1 is the second row, okay? And now we will rearrange this summation with respect to the measurement operators. Okay? So the first term is about this measurement operator M0 plus. The second term is about M0 minus, and so forth. Okay? So if you think about the first term here, so this is actually the probability that M0 plus detecting this unnormalized state. Okay? And the similar thing is true for all the others. So if we normalize these terms here, so if we can make this one as a normalized state, then this one is the probability of this measurement detecting that state, normalized state. Right? And similar thing is true for all the others. So we're going to normalize those states. So this one, so we will use the notation rho tilde, which means the normalization of these. Okay? So for the case when omega is 0 plus, then this normalized state is nothing but this one over the normalization factor here is eta 0 plus eta 1. Right? And yeah, same is true for all the others. So we have another set of states which consists of these rho tildes. Okay? And we also use that normalization factors as the probability distribution for these induced states, rho weak. Right? And the normalization factor here is eta 0 plus eta 1. But if we can see all the normalization factors, eta 0 appears twice here. And eta plus as well. Where is it? Twice here. So if we sum up all the normalization factors, it's sum up to 2. So to make them as a probability distribution, we have this factor half here. So we have new probability distribution for this new set of states, rho tilde, and the probability distribution is half times these normalization factors. Okay? Then we can consider this success probability with pi as the success probability of another state ensemble consisting of eta tilde and rho tilde. So what I want to say here is that any state discrimination with pi can be considered just the state discrimination of some different ensembles. Right? Okay, so this is what I've just said. So for epsilon and epsilon tilde, we share the set of average states, normalized state, and this probability distribution. So we have seen that the state discrimination of epsilon with pi is equivalent to the state discrimination of epsilon tilde, in the sense that these two success probabilities are always equal to each other with respect to the same measurement operators. Okay? And of course, the maximum success probability will be the same because we are talking about the same measurement operators. And maximum is just over all possible P of EM. So the maximum probability, success probability with PI, this one, PGPI, is maximizing this. And also it's maximizing this one, which is twice of PG of epsilon tilde. Right? And of course, similar thing is true for the case of LOCC measurement. If we maximize this success probability of all possible LOCC measurement to obtain PLPI, which is same with this twice of PL epsilon tilde. Okay? Okay. So as mentioned before, obtaining an upper bound of PL or PLPI is important because to obtain the exact value of PL or PLPI is usually hard. And by using this relation, we can have this lemma, which is about the upper bound of PLPI. So for given set of ensemble epsilon, this H tilde is a Hermitian operator satisfying these properties. Then, this twice of trace H tilde is an upper bound of PLPI. So this is nothing but using the previous proposition to obtain the upper bound of this PR. And if we just multiply by 2, and we obtain the upper bound of this one, which is the upper bound of this one. let's watch this. What this lemma is about. Okay, so let's have a look of some examples. So first we're gonna see an example which shows locking NLWE by PI. And let's recall the definition. So the locking NLWE by PI is the case when there was NLWE in the first place, but NLWE vanishes if PI is available, right? And this is the example we consider here. It consists of 4 states, row 0, 1, plus, minus, which are our product states. And the probability, the corresponding probabilities are here at a 0, 1, plus, minus. Okay? And of course, there are 2 sub-ensembles. First one is by these 2, row 0, row 1, and the second sub-ensemble is with these 2, row plus and row minus. Right? So to see the locking, the phenomena of locking NLW by PI, we will evaluate the explicit value of this PLPG, PLPI, and PGPI as well. So we're going to use the propositions and the lemmas that we introduced to obtain these values. Okay, so for PG, the proposition 1 was about PG. That's like this. If there is a P of EM satisfying this for all indices, then this P of EM realizes PG, the maximum success probability of all possible P of EM. Okay? So we're going to use this. And let's consider this measurement here, M0, 1, plus, and minus, which looks like this. Here, mu plus minus and gamma 0, 1 are like this. Okay? Then, by straightforward calculation, we can check that this measurement satisfies the conditions of proposition 1. Okay? It's to check the positivity of these operators.
So where did gamma come from?
You mean how we get this?
Yeah, gamma enters somehow, and I just missed that.
Which one?
Gamma.
So we are considering this measurement.
Oh, lowercase gamma.
Yeah. This one. Lowercase gamma. Oh, I see. So gamma is from the definition of the examples. Gamma is between 2. Any gamma between 2. Any gamma larger than or equal to 2.
So it's parameterization of probability.
Which one?
Parameterization of probability.
Yeah.
Yeah, single parameterized.
Yeah, single parameter. So this example 1 is actually a set of ensembles parameterized by gamma. So it doesn't matter which gamma you consider. As long as gamma is larger than or equal to 2, we can see the phenomenon of locking NLWE by PI with this example. Okay? So, right, so we're here. So if we consider this measurement P of EM, that we can directly check that the property of proposition 1 is satisfied by this measurement. That means expectation with respect to this measurement operator will give us the guessing probability. So if we evaluate that, the guessing probability is like this. Yeah. So it's just a straightforward calculation. Okay, so we have PG here by using proposition 1. And let's think about PL. Okay? As mentioned before, PL is hard to get. So we're going to consider an upper bound and a lower bound which are equal to each other. That means we have PL. Okay? One lower bound here can be obtained by considering this LOCC measurement. So this is trivially LOCC, right? Because the first, it can be done by performing sigma z on the first subsystem. And then depending on the measurement result, we will perform sigma z or sigma x on the second subsystem. It's actually one round LOCC measurement. One-way LOCC measurement. Yeah, because the ensemble of our consideration in example 1 is this, we can just evaluate the expectation with respect to this measurement operator. Because this is LOCC measurement, the expectation is lower bound of PL, because PL is the maximum overall possible LOCC measurement. So we have this P on a lower bound of PL. To obtain an upper bound, we use proposition 2, which was like this. So if there's a Hermitian operator such that every operator here with respect to this I is in SAP star, then the trace of H is an upper bound of PL. Okay? So we need to find a Hermitian operator H satisfying this. But before that, let's think about some properties of SEP star. Okay? So the first thing we can easily see is the following. Any positive semi-definite operator is in SEP star. Right? Because if A is positive and B is any separable positive operator, a positive semi-definite separable operator, and trace AB can be written like this. So A is positive, so it's just square of square root A, and B is square of square root B. Then in trace, we can just move square root A from here to here. Then the composition of the last two is nothing but the Hermitian conjugate of the composition of the first two. Okay? So we know that any operator of this form is positive semi-definite. It's like A dagger. So the trace is always non-negative. That means any positive operator A is in SEP star. Another one we can see here is that if A is PPT, that positive partial transposition, that has positive partial transposition, that means partially transposed operator is positive semi-definite. Then we can easily see that A is also in SEP star, because trace of AB is invariant under the trace of partial transposition of AB. We can easily show this, right? So if A is PPT, that means A gamma is the partial transposition of A is positive, and B is what? B is separable, right? Yeah, and separable operators, which is trivially PPT. So B partial transposition of B is also positive. Both A gamma, B gamma are positive. So from the first property, this one has positive, non-negative partial trace. Non-negative trace. Sorry. And of course, trace is closed on the linear combination. Yeah, in this case, the linear combination of non-negative coefficients. So any linear combination of these positive operators or PPT operators with non-negative linear coefficient is closed. Okay, and it's also in this SEP star. That's what we're going to use later. So, so the Hermitian operator of our consideration is this H. Yeah. So where sigma 0 is the identity in one qubit system, and sigma 1 is nothing but sigma x. Okay. So this is trivially Hermitian. So the only thing we need to check is whether this one satisfies the properties of proposition 2 here. So by using this H, we can think about these four operators. And we can rewrite these operators like this. Okay? So we can clearly see that the last two is positive semi-definite because lows are always positive. So positive operators, so these are in SEP star. And the first two can be written as the linear combination of is T0, T1. So here, T0 is this one, and T1 is this one. So for the range of gamma, in this range, this is always positive, semi-definite operator. So this is a linear combination of positive operator, and partial transposition of positive operators. So this is PPT, right? If we take the partial transposition again, this one just becomes T0, which is positive. Okay? So this is linear combinations of positive operator and PPT operator. So this one is in SEP star. Okay, as mentioned before. So we use these properties. And same is true for the second operator here. So all of these four operators are in SAP star. That means trace H is an upper bound. Okay? And if we evaluate trace H, this is this value, which is actually the lower bound we obtained before. So we have the same upper bound and lower bound. So we have PR here, which is this value. So as mentioned before, it's hard to get this PR, but if we can use upper bound or lower bound wisely, we can get this PR. Right, so PG we have already obtained before, which was this, and PR is this. You can see that these are, this one is strictly less than these two, as this one. So we have non-locality without entanglement in this ensemble of example 1.
Sorry, 10 minutes remaining.
10 minutes?
Yes.
Okay. Sure. Yeah, that's what I want to know, actually.
Including questions.
Yeah, including questions.
Okay, so, right. Then, yeah, let's go. So about PRPI, we can obtain a lower bound, which is 1. And it can be obtained by these measurement operators. Okay, it's the following. So if row 0 is prepared, then you can see that these two are orthogonal to these two. Okay, so the only measurement operator that we can detect is either M0 plus or M0 minus. And because we're going to get the post-measurement information about the state row 0, which is in the first sub-ensemble, we will just focus on the first coordinate, which are 0. So we can determine that the prepared state is row 0. Okay? And the same is true for all the other states. So we can always discriminate what the prepared state is with certainty by using this measurement. And this is also clearly LOCC measurement. This is nothing but, measuring sigma x on the first system and sigma z on the second system. Okay? So by using this LOCC measurement, we have a unit probability. That means, which is a low bound of PRPI. So everything is equal to 1 in this case. So, yeah. So PGPI and PRPI are equal, which is 1. So there is no non-locality without entanglement. Yeah. In this case, if the post-measurement information is available. So the situation is like this. So for the example 1 that we consider, in the first place, without post-measurement information, we could see NLWE. But if the post-measurement information, so this one means the PG and this one means PR. Actually, we obtain the actual values. This is just the graph. Okay? But if the post-measurement information is available, PGPI and PRPI are equal to each other. That means there is no NLWE. So example 1 shows locking NLWE, locking NLWE by PI. Okay? Right. So the second example is about unlocking, but as now mentioned, I don't have enough time, so I'll skip the second example. Okay, so let's summarize. So here we introduced the concept of locking and unlocking NLWE by PI, and we show some examples with explicit values of PR, PG, PRPI, and PGPI. Right? Even though we didn't see the example 2, example 2 is actually the first example known ever for the case when NLWE is NLWE occurs with PI, and the NLWE is in perfect discrimination. That means this PGPI is 1 and PRPI is strictly less than 1. So there was no such example known before this one. And these are some possible future works. How many minutes do I have more?
Yeah, 7 minutes for questions.
Sorry?
7
7
minutes
minutes,
for questions.
okay. Right, so let me briefly talk about this future work. So first, we have talked about locking and unlocking NLW by PI with respect to the minimum error discrimination. But there are some other state discrimination strategies rather than just minimum error discrimination. So it will be an interesting future work to think about this NLWE scenario with respect to some other measurement strategies. And the other one is, we have talked about possible upper bound of PL, which is very important. So it's an interesting feature to think about to obtain a good possible upper bound of PL. And the third one is, actually we have seen some examples where locking and unlocking NLWE happens, but we don't really know yet what is the general condition for a given ensemble having locking or unlocking NLWE by PI. Right? And the last one is, yeah, so in this talk, we only talked about LOCC measurement and see the difference between global POBM and LOCC measurement. We can also think about some other constraint on the measurement. Okay, for example, we can think about separable measurement or local operations and one-way classical communication measurement. And look up and think about what this NLWE phenomenon will happen with this constraint of measurement. Okay? So I guess that's it. Thank you for your attention.
So we have 5 minutes for questions. If anyone has any questions.
I have a question.
Sure.
Thank you for your interesting presentation.
Okay.
Do you think that there is a connection between the maximum value of PG of epsilon and the quantum discord of ensemble epsilon?
Quantum discord of ensemble epsilon. Yeah, I guess it's a good question. So, so this is non-locality without entanglement, but your question is whether or not there is any other possible correlation.
I was trying to figure out if this non-locality that we're talking about could be somehow quantum discord, which people have studied earlier.
See. So, so if you see the state of our consideration, this is just the product pure state. So there is no discord.
Actually, I see. Like, since we cannot completely distinguish between one and the rest, so there could be a little bit of discord.
So discord of what are you talking about? Discord of these states?
On the ensemble itself.
Oh. So I'm talking about, so I was talking about entanglement of the states here. I was not talking about the entanglement of the ensemble because I don't really know how to define the entanglement of an ensemble.
Right, but we can define, if it is a two-partite system, we can define quantum discord for it.
For an ensemble, not for a state. Are you considering the ensemble as a quantum state or just?
As a, like a density of
no, it's not the case. I'm not talking, we are not doing that. So this is just ensemble.
Okay. But what about, for example, this example? Something that comes to my mind is that there's one condition that can give us PG and PL being equal. For example, if a state is separate, not entangled, the ensemble is not entangled, and also the quantum discord is 0, then PG and PL will be equal.
So the state is not, sorry, the ensemble is not entangled. You mean if you consider the ensemble as a quantum state, it's not entangled.
Yes.
That's what you're talking about. So how do you define the ensemble as a quantum state? So that's just a mixture of these four with this probability, right? If you think about the mixture of these four with these probabilities, okay, it's again a separable state. So there's no entanglement. And what about this code? Yeah, this code would be different. So each of these states here doesn't have any discord. But if you think about the mixture of these states, there might be some discord. Yeah. So for your question, if you think about the ensemble as a quantum mixed